Alrighty, so this is part B1 of exam 3. And for this part, we're going to be going over how to find and create the differential equations for the molar fractions of the water, the temperature of the air, and the temperature of the gas stream differential equations for a cooling tower. And so starting off, we're going to want to give a representation, a visual representation of what we're actually looking at. So right now, this is going to be a cooling tower with a small section of packing labeled A. And we're going to define that up here for the direction, z is equal to 0. And traveling in a positive downward direction to distance z. And we are also going to have flows of, and I'll just type this so it's easier, and I'll explain what these each individual arrow represents here in a second, but they are essentially flowing like that. So this one going into on the left side, that is TW, which is the temperature of the water going in. And you're also going to have TW going out. Here on the right side going in is going to be TG, which is the gas going inwards, which is the feed. And then you're also going to have TG going outwards here at the top. Some other things we want to know is we're going to define capital L as the gas flow, or the liquid flow rate, which is in, I'll just type this out, liquid flow rate, which is in kilograms per meter squared. And then we are also going to have capital G being the gas flow rate, which is also kilograms per meter squared of the respective gas and liquid. So carrying on, we're going to want to start deriving the actual differential equation, and we'll start with the mole fraction. So the first thing we're going to want to do here on the left-hand side, obviously it's supposed to be lowercase d. All right, just pretend that's a lowercase d for the differential equation. The difference of what I'm about to type. So first we're going to have here the gas flow rate times capital A, which is the area, times the mole fraction all over the molecular weight of that respective water, that is. And we should know that the molar flux is going to be in moles of water vapor in the air, which is why we have to include that mole fraction. So that is the right-hand side, or left-hand side. Let me see if I can turn this into an equation real quick, just to make it look more proper. All right, there we go. Although this whole thing is supposed to be, let's see. I'll just retype this because I want to clean it up a little bit. GAY over M. Alright. So now that we have that, we want to go over the right-hand side of this differential equation. Which is going to be, in the outside, it's going to be Kc, which is the mass transfer coefficient, times, and I'm going to come back to that part just for more explanation. And this is going to be times the difference between the concentration at the interface of the area we're looking at minus concentration away from the surface. So we're going to use nope, that's not what I wanted. or maybe it is. Then we want infinity. There it is. Times A, which is the specific area. It should also be noted that the within these parentheses here, that the units are going to be kilograms or moles per meter squared per second of water. So times A is specific area times capital A, as I already stated, that's the area, dz. So that AdZ here on the end is going to be the differential volume. And when it's multiplied by the specific area, that is going to be equal to the total surface area. So let me make this a little bit bigger so you can actually see it. I should have done that from the start. There we go. And like I said, I wanted to come back. The one thing that we didn't put in right away is a negative sign from the KC. And that is because, as you see here on the right-hand side, we defined that the direction is going downwards in a positive, or that is the positive direction going downwards. And when you have that mass transfer coefficient going upwards with the feed, that is in a counter direction. So that is why we make it negative. So moving on, we want to define now is the molar flux of the water vapor in the air between the surface. And this is going to allow us to simplify this equation I just derived furthermore. So that molar flux is going to be equal to Kc. Once again, the mass transfer coefficient times the difference in concentration. I'm just going to copy and paste this. Which this is going to be all equal to Kc again times the saturated water vapor of the partial pressure of water at a temperature of the water. And that's going to be minus the mole fraction times the total pressure, and that is going to be all over RT. So now that we have that, we can simplify this top equation even further. So we have dy dz being equal to negative specific area times the molecular weight, and I should capitalize this just to keep it consistent, times that molar flux all over G, which is the gas flow rate. So that completes our differential equation for the mole fraction of the cooling tower. Alrighty, so now we're going to be doing the differential equation for the water in the cooling tower. So in doing this, I'm going to insert an equation real quick. And what we want to look at here first, if it's going to let me type. Alright, I think I just, okay. So what we want to first look at here is the change in enthalpy. So we're going to have dHW, which is the change in enthalpy of the water, which is going to be equal to the area times the liquid flow rate, capital L, times CL, which is the heat capacity of the liquid phase, times dTW, which is the differential temperature change of the liquid water. So now that we have that, okay, we can then carry on and say that this is all equal to, let me insert another equation. So this is going to be equal to H, which is the heat transfer coefficient, times the difference in temperatures, which is temperature of the gas phase minus the temperature of the water. And I should say that is the temperature of the air in the gas phase, and then the temperature of the water. And then everything, this difference here is going to give us watts per meter squared in units. So we are then going to want to multiply this all by what we found beforehand in part 1, and that is that total surface area of the process area that we were looking at. So you're going to have that specific area times capital A area, dz. And I'm going to put this all in parentheses real quick, because this first part here, that is going to be the heat transfer of the air to the water. And then we're going to subtract that by the evaporation occurring. So we are going to have the enthalpy of vaporization, get brackets in this, enthalpy of vaporization times NW, which is, like we found before, the molar flux of the water vapor. This is going to be times that, that total surface area again, A dz. Let me elongate this a little more. Perfect. And then this is going to help us all find, and like I said, left side here you have we have the heat transfer of the air to the water phase, and then on the right side we have the evaporation going on from the water to the air. And it should also be noted for units that the specific area is going to be in meters squared per meters cubed. So this all lets us find, just knocked over my mic, it scared me a little bit, is going to allow us to find that the final differential equation that we want is going to be dTW, change in temperature of the water, dz with respect to distance, is going to be equal to the specific area divided by the liquid flow rate times the heat capacity of the liquid phase times what do we want? We want the heat capacity times that temperature difference, Tg minus Tw, minus want the enthalpy of vaporization times NW, the molar flux of the water phase. So that is going to be our final differential equation for the water in the cooling tower. Alrighty, so now we're going to be finding the differential equation of the air in the cooling tower. And to do this, we first want to analyze a drawing that I'm going to make here of a zoomed in picture of the packing within the cooling tower. And I'm just going to draw it here on the right hand side. So we have the packing, it's in that section with a distance of dz, change in distance, and you have obviously the flows coming in and out, which is going to be the enthalpy of the water coming downwards direction, and then on the right hand side you're going to have the enthalpy of the gas going in an upwards direction. So if we just look at the change in enthalpy in a downward direction, we would have the enthalpy of water minus enthalpy of gas. We know that that's going to be equal to a total of 0. So if we set it equal to 0, we know that the enthalpy of the water is going to be equal to the enthalpy of the gas. So in knowing that, we can then start deriving this equation. I'm just going to carry this on. So we got water, or the air, excuse me. We just found the water. So the air now, let me insert an equation. So now we have that. We want to start deriving this equation. So we know that the air is going to be equal to the gas flow rate times the area, which is going to be This is going to give us kilograms per second, and then we can then multiply that by the heat capacity of the gas, or the vapor that is, times the temperature of the gas. And this is going to be, let me add in another parenthesis real quick. And then this is going to be, obviously that's the vapor phase, plus we have, once again, the gas flow rate times the area times the enthalpy of vaporization, delta, or not delta, lambda, times Y, which is the mole fraction. And this is going to be divided by the average molecular weight. And what we know is that this whole right side is in moles per second. So what we want to do is we want to get or convert that, what do I want to say, the water vapor here, which is why we include that mole fraction. So, okay, that looks good. And now we can continue carrying this out. So what we want to do here is take this whole side that we just found, and we're going to set it equal to, let me get that out of there real quick. We're going to set that equal to what we found here in part, or in doing the gas differential equation in the cooling tower. And we can set that equal to each other. Let me see if I can get this fitted in one line. There we go, and you can see it good. Okay, so now that we have that set equal to each other, we can then cancel out the area for each one, and then we're also going to want to divide both sides by this dz. So when we do that, we then get d, didn't want that, got to insert equation again, try to slide this over a little bit, too much. So we're going to get d, or actually we're already taking the change. So we have the gas flow rate times the heat capacity of the gas times the difference in the temperature of the gas, which is going to be over dz, since we divided that over. Okay, and that is going to be plus, since we're still on the left hand side, we're going to have that lambda, that enthalpy of vaporization, that is, times the, and we know, we already defined that the gas flow rate divided by the average molecular weight is a constant, times, we'd have that change in the mole fraction, dy, dz. Okay, and that's going to be all equal to the right hand side now. So we have that specific area times the heat, forgetting the name of this just randomly, heat transfer coefficient, and that's going to be times the change in that water or that temperature difference, which is the gas and the water temperature, minus the enthalpy of vaporization again. And we can slide this over just to see it. Enthalpy of vaporization times that molar flux of the water vapor times the specific area again. So that leaves us to the final differential equation. So we're going to have dTg, the gas phase, over dz, respect to distance, being equal to, you're going to have the specific area times the heat transfer, the heat transfer coefficient, I don't know why I keep blanking on that, divided by the gas flow rate times the heat capacity of the gas flow rate, and that's going to be times the difference of temperature, so the gas flow temperature minus the temperature of the water. So that is our final equation, the differential equation for the air, and that completes part B1 now that we have found all three parts, all three differential equations. Alrighty, so now we're going to be doing part B2 of this exam, and what we're going to do here is now take those differential equations that we just created and create tabulated data with that, and create some scatter plots with the data that we're about to integrate. So starting this off, we want to start with an import numpy as np, because numpy is a Python language library that we want to import and use, which will help us solve arrays throughout this this video here. Next, import again. Actually, now what we're gonna do here is change the background of the scatter plots that we're gonna be making, and how we do that is with these two steps that I'm typing out here. Templates default, because the default here is typically a white background, but we can change it to a black one to make it stand out more. Actually, I don't want that. Next, from plotly.subplots, and what this step is doing here is going to create, oh, hold on, I don't think I ever closed out the parenthesis or the quotation. Alright, now we can, from plotly.subplots, and what I was saying is that this is going to allow us to create our graphs at the end based off of the data we can calculate. So from plotly.subplots, and then we want to import make subplots. Next, from scipy.integrate, and what this is going to do is solve initial value problems based off of the ordinary differential equations that we give. So import solve IVP. And then lastly, what we want is from scipy.optimize, and then this is going to calculate any roots of the value problems that we give based off of the vector functions. So from scipy.optimize import, this is where we import any roots, or it'll allow us to. So I think that should be good. Make sure it runs okay. All right, we're good. We're good. And so, okay. So next, what we want to do is define a function that we may want to calculate, which in this case is the vapor pressure of the H2O. So we're going to define, we can call this PV for vapor pressure, or VP, whatever, it don't really matter. Temperature, which is the function, and then as it's indented, we want to return this value, and we're going to give it the formula that we want to use. So it's going to be 10 what's the value? 8.0 7131, yeah, minus 1730.63 divided by 233.426 plus T minus 273 to convert from kelvins to Celsius. Yeah, I think we need that many parentheses. Divided by 760 for atmosphere, converting into pressure, 101.325, which is a known basic unit. So run that, invalid syntax. I think one too many parentheses there, actually. All right, now we're good. Alrighty. So I realized here when that syntax error came up, what I was actually missing was, and I needed that third parenthesis there, but I was missing the first bracket in front of that to make sure that we included this whole section here in the denominator of the equation for the vapor pressure. So I just went back and fixed that real quick, but that is it. Moving on, we want to define some variables now that we're going to be using here in our differential equations and throughout this code. And I do have some of the given constants in the problem written down here on the side that I'm just going to be referencing. If it looks like I'm looking at something, that's what it's going to be off to my side here. But besides that, I'll be given variables here. So to start, we can use, or we can start with the heat transfer coefficient, which is going to be lowercase h, which we know given to us is going to be 10 watts per meter squared Kelvin. So 10, yeah, looks good. And then just to signal what units it is, watts per meter squared Kelvin. There it is. Next, what we want to do, maybe that gas constant R, which is equal to, I believe, 8.0 or 0.314, and that is hashtag, what is that? Joules per mole Kelvin. Then we could get into maybe like the heat capacities, which looking up previously, we can do like the heat capacity of air. So C air is equal to 1,000 joules per kilogram K. Forgot the hashtag. Joules per kilogram K. Then we can do heat capacity of water, yeah, G with gas, which is equal to at 2,000 joule per kilogram K. Last, we want to do the heat capacity of the liquid, WL, or maybe we do capital L, which is equal to 4190 joule per kilogram K. Next, we can do the maybe like the density of air. So we can just say rho air is going to be equal to 1.2 kilograms per meter cubed. Hashtag. Next, we can do the enthalpy of vaporization. So HV. Actually, I don't like the, well, yeah, HV, which is going to be equal to, what is that, 4,700 joules per mole. And then finally, we can do the mass transfer coefficient, Kc, being equal to, and we can calculate that using the formula of the heat transfer coefficient divided by the density of the air times the heat capacity of the air. Some other stuff we may want to incorporate. This could include what we know the specific area, which is represented by the A, given to us, that was 5 meters squared per second, or per meter cubed, excuse me. We know the molecular weight of water, just by definition, is 18 e to the negative 3, because we're going to convert that to kilograms per mole. And then we also know the molecular weight of air being 29 negative 3 kilograms per mole again. What was also given to us is the velocity of the air entering the system. So we'll call that velo, equaling 5 meters per second. We also know the liquid flow rates, which was given to us at 0.5 kilograms. Is it kilograms? Yeah, okay. Kilograms per meter squared seconds. Finally, we also know the total pressure, P, being equal to that 101,325 that I use in defining the what's it called, the vapor pressure. And come to think of it, I'd actually mess that number up, 101,325. So let me run that again. I'm trying to think anything else I might need. Okay, so we also know the height was given to us. I'm not going to use h because that was the heat transfer coefficient. So height was 20 meters. We also know the temperature water feed is going to be equal to, given to us at 70 Celsius, plus the 273.15 to convert to kelvins. And then we also know the air temperature feed. This is going to be equal to, what was it, 25 was given to us, plus the 273 again, plus 0.15 Kelvin. Lastly, the mole fraction of air feed, and that's going to be equal to 0.5 because of the 50% humidity, times that vapor pressure, PV, times the TA feed divided by the total pressure. We also know the air flow rates, which is equal to, it is the total pressure times the air, or molecular weight of air, divided by the gas constant R times the TA feed, and then all times the velocity. And then one other thing we want to do, I'll just describe as I'm typing this out. So z underscore plot, which is returning, I need to finish typing this all out first before I explain it, is equal to the np numpy dot linspace from 0 to the height. So what this is going to do is give us some, as you can even see how it describes here, is return evenly spaced numbers over a specified interval. So starting from 0 to the given height, which was 20 meters, you're going to have 21 evenly spaced values from 0 to 20 meters, which is what is going to be produced under Z plot. So now that we have that, we can then go on and say we also want the initial guesses for our solve IVP that we will eventually be doing. So we want to do the mole fraction exit guess. So as I described it, that's going to be equal to YA feed and then multiply by now, so since we're doing an initial guess, we know that the exit is going to be greater than the feed entrance, so we can literally multiply this by anything. So what I'm just going to multiply by 1.1 just as our first guess, and then we also want to do the temperature of the gas exit guess, which is equal to the TA feed, that air temperature feed, and then once again it's going to be greater than the actual feed, so we can literally guess like 1, 2, 3, anything, but just something in the middle. We'll go with 5, and then finally, to cap this off, we want to say sol for our solution is going to be equal to none, so that there's nothing left in our solution once we go through our solve IVP. So let's just evaluate this. Okay, it ran well. So now that we have our initial guesses, what we want to do is define a function whose roots we can find, and once it converges at the end, we'll know that it is done. So what we're going to do here is define, I'm not even typing yet, define converge, as I said, and what we're looking at is the temperature feed for Y, for the mole fraction. So converge underscore feed of the air underscore of that TY, and what we want to do here is evaluate it at the outer scope. So it would normally be just V, but we're going to call it V2 in this case. So V2. Once we have that, we can now evaluate like the exits that we just did up above. So Y exits okay, I only need that part. Y exit is equal to that V2 bracket of 0, because that's 0, is the first value we want to evaluate, and then we want the TG exit for the second value, so that's at 1. Now that we have that, we want to, so it's kind of trapped within its own function right now. So to extract it and to be able to evaluate it while saving time, we want to use the global function. So global sol, the sol variable being the solve and the solve IVP that we will create. So now that we have that, and like I said, it's that outside scope we really want. We can then define our functions here for our differential equations. So we know that it's dy for the differential mole fraction, TW, and TG for the gas, at Z for distance, and V for the inner scope. Now that we have that, we can then evaluate each differential value. So y is going to be equal to the inner scope V for the first value 0. Then we have the TW evaluated at V for the second point, and then TG, which is going to be evaluated once again V inner scope for the third point of for 2 there, that is. Now that we have that, we can then go and define more variables. So we want to start with the gas flow rate of water, which we know from deriving that is the mole fraction Y divided by 1 minus Y. Okay. Then it was times the G air, which is the gas flow rate of air, times the molecular weight of the water, which we already know for both of those, and that is going to be then divided by the molecular weight of the air. Next, we want to define the total gas flow rate, which we know is just going to be GW, the gas flow rate of water, plus the gas flow rate of air. Okay, there we go, wasn't it? And okay, and then we want to define the total average molecular weight, which is going to be equal to G air, the gas flow rate of air, plus GW, gas flow rate of water, divided by the gas flow rate of air, plus the gas flow rate of water. No, that's not right. Divided by the molecular weight of the air. Yeah. And then we want to do, oh yeah, plus the gas flow rate of the water divided by the molecular weight of the water. And let's just add some spaces to give it more clarity. Okay, good. And I think that's it then. Lastly, we can do the heat capacity of the gas, which is going to be equal to the heat capacity of the air times the gas flow rate of air plus we want the heat capacity of the water gas times the gas flow rate of the water. Yep. Okay. And that's going to be all divided by the total gas flow rate. So have all that good. And then I think all we have to do is execute this now. Oh, I just forgot a colon. Let's try this again. All right, it ran that time, so good for that step. So now we want to input our differential equations that we know. So starting with the molar flux of the water vapor between the in the air, we derive that equation to be NW is equal to the heat capacity Kc. Let me make sure I didn't capitalize the K. And okay, yeah, I did capitalize it, Kc. And that's going to be times no, that's not times. Divided by the gas constant R times, or divided by the gas temperature going in times the vapor pressure we found times the water temperature. Not the feed though. Minus Y, which is the mole fraction, times the total pressure. Now that we have that, now to the actual differential equations. So the differential of the mole fraction, dy, is equal to that negative A, that specific area, times the molecular weight, average molecular weight, divided by the total gas flow rate, times that molar flux that we just wrote the equation for above. Next is the dTW, which is the differential water temperature of the cooling tower, which is equal to the specific area divided by the liquid flow rate divided by the oh, that's not what I wanted. Divided by the, oh, okay, there we go. The heat capacity of the water liquid flow rate. Let me just make sure I define that up above, CWL. Okay. So now this is going to be times the heat capacity, or not heat capacity, heat transfer coefficient, times the difference in the temperature, which is TG for gas, minus T water, and that's going to then be what's next is subtracted from it, which is HV, which is that enthalpy of vaporization, times the molar flux of that water vapor. Next, dT A or G for gas, that's going to be equal to the specific area times heat transfer coefficient divided by the total gas flow rate times the heat capacity of the gas times the temperature difference, which is TG minus TW, forgot parentheses there. And then this is, I think that's it for that. And then lastly, we want to return these values. So return dy, dTW, and dTg. So then we can actually input our solve IVPs. So now we're going to incorporate the solve IVP function into this. So in doing so, I'm just going to type solve IVP, and then in parentheses, what we start with here is our function, which is our callable, which we're going to call it dy tw tg for our differential equations. And then next we want our independent variable, so 0 comma the height that we were given, and then next we want our initial states, our initial values. So we want the y exit, the tw feed, and then you also want the that TG exit that we guessed from above as well. So TG exit, that, and then comma. Next you want your integration method. As you can see, they use RK45. We use Radow, so that is Radow, comma, and then computing for a continuous method, we want to do dense underscore outputs is equal to true, and that's going to be dense sol at z underscore plot there. So, and then we want to return this, so return sol bracket, we want to do 0 for the first set of our values to -1, which is the last of the fraction. And then we want to subtract the YA feed, I believe. Yeah, okay. And that's going to give us one of our roots. And then we also want to do sol 2, comma, -1 for the gas phase there. Same principle though, wanting the last value for the -1 minus the TA feed. And then I think we should be able to run this block here. Okay, that worked correctly. So now we want to store this solve IVP as sol for the solution. And then just make sure that it's in line correctly, so now we can store it under sol, and it is. Alrighty, so now we want to call our root that we have been looking for this whole time. So in doing so, we're going to do root, and then we want to call our converge that we had right up here, this function. So converge underscore feed underscore air underscore t y for our callable, and now that we have that, we can then continue on. Actually, no, wait, yeah, ty comma, and then bring in our guesses. So y exit underscore guess, comma t g, that exit for the gas temperature guess, and then that should be it for the root. So we can display that, and I think those are good values right there. -27, 1.14, and 0.045 negative. And it says the solution has converged there. So yeah, I think that is good. So lastly, we want to plot this. So we're going to do figure equals make subplots. Then we want to import how many rows and columns for like where the graphs are displayed. So for this, we want 3 different graphs. So I'm going to say for rows, that's going to be equal to 3. And for columns, yeah, calls equal to 1, just so they're in one column there, but stacked on top of each other. Now that we have that, we then want to do fig.add trace, add scatter first. Actually want to import the scatter plots first. So we want to plot like each of those independent variables that we have, which were up there, as you can see. So we're going to say x is equal to z underscore plot, which we defined before, and that y value being equal to the sol of the sol value p of 0, the first term, colon, comma, and then we're going to define a name for this. So we want to call it, the first one, we'll just do the mole fraction. So y, the mole fraction of water, so H2O, and then define which row and column we want. So row is equal to 1, comma, column is equal to 1 as well, and that should be good for that. Oh crap, did not mean to do that yet. Well, I guess that's glad we see it's working all right. So next we want to do the same thing now for the other two differential equations that we did. So fig.add scatter x is equal to, actually I'm just going to copy and paste this to save some time. We'll just have some stuff we have to change around. So x equals z plot, we want 1 here for the second part of it, and then instead of y H2O here, we can just call it TW for water temperature, and then we want rho equaling 2 there instead of 1, and I think that should be good. And then same, oh, forgot I didn't copy the whole thing last time. So this time the second one for the third section that we want there, G now instead of W, and row 3 instead of 2. And then lastly we can adjust, let me see here, let's just see how it's looking. Alright, so we have our 3 graphs here, but what we're going to want to do is, you can see like the, what do I want to say, the spacing for the x and y axes are kind of lopsided. So to change that, what we are going to do next is do a fig update for the scatter. So fig.update, and the layout, that is. As you can see, that's one of the options here, fig layout. And what we can change next, we want to change the width to be equal to, we want it 600. I think that's, we'll make it shorter. And then length, oh wait, that's not a, okay. Height, yeah, there we go. Equaling 800 maybe. Okay. And let's just see it now. Okay, that's somewhat better. And then you can just, we can mess around with the dimensions. So we can go higher maybe on the height to like 900 and see how that goes. So shift enter on that. Okay, looks a little bit better. Maybe go up to even 1,000. See how that's looking. Not 100 or 10,000. We don't want that. Boom, boom. Looks good. So regardless, you can see you can mess around with the width and the height. We'll just leave it at that for now. Kind of went over, but as you can see here, the blue line represents that mole fraction of the water. You've got the red line showing the decrease. The water temperature of the cooling tower, and then we have the green line being the gas temperature of the cooling tower. So yeah, I think it looks pretty good, and that should be it for this video then.